thanks everybody for coming. For those who are here the first time, let me just say a few words about what this room is for, and what the heck we're doing here. So this is a regular bi-weekly meeting, and we mostly focus on low-level performance and everything related to that. It's like how to analyze and find performance bottlenecks in your application. We talk about hardware, operating systems, compilers, high-performance libraries, programming models, and so on and so forth. Performance is a huge topic, right? And it's very complicated. But that's great that we have people with so you can consider it as a place for sharing ideas, and this is actually a primary goal for me. This was a primary goal for me when I just decided to organize this Twitter Spaces room. And this is personally, for me, it's a great place to learn from all of you guys. And I want to keep the mic open, right? So feel free to request the mic if you have something to say, obviously, but please be mindful about it. So remember that I encourage everyone to speak, but please be mindful. All right. So we have Nadav Rotem joining us today. So Nadav works as an engineering director at Facebook. Over the years, he has worked on compilers for many languages, including C++, Swift, and JavaScript. Nadav is the original author of the LVM Vectorizer. In addition to compilers, Nadav worked on systems in the area of machine learning, high-performance computing, and FPGAs. Hello, Nadav. Welcome.
Hi.
I'm excited to have you.
Hi, Dennis. Yeah, it's good to be here. Thank you for inviting me.
Sure. Yeah, absolutely. So let me start with the question that actually interests me the most.
Okay.
And so the question is, so Nadav, you obviously worked a lot with the LVM compiler, right? Yeah. And LVM compiler is very mature infrastructure, and not many new optimizations being added nowadays, right? But still, people always want more performance from it. So how do you think? How much potential for improvement we have in existing LVM passes?
That's a hard question. I don't know. There are a lot of smart people who are working on this problem. I think that we still have some room for improvement. I feel like it's going to have, at this point, it's going to have to be a combination of changing the workloads and changing the compiler. When you look at the quality of the generated code, a lot of times you're telling yourself, well, the code looks pretty good. I'm not sure what else the compiler can do. I mean, there are a few places where the compiler is not doing a good job. And I can give you a few examples. Let's say that you write a simple loop in C. The compiler is most likely do a really good job in allocating registers, getting rid of redundant code, and so there's no much room for improvement there. But there are areas where we have complex library code, heavily templated code, where the compiler may not be aware of the semantics of the library, or may have to deal with too much code so that the inlining decisions may not be optimal. And there, I think that there are some opportunities. But again, there are many smart people in the space, and they all have different ideas. And it's not easy to get more performance.
Yeah, it's true. So it's actually funny. So there is a Probsting law. So which says that performance of the generated code by compilers doubles every 18 years. And actually, yeah, and some believe that this number is even higher than somewhere around 50 or so. So do you share this sort of pessimistic view, or you're more optimistic here?
Well, I think it depends on the workload, because sometimes you just get, if you get the loop right, then you get the loop right, and there's nothing else that you can do. I think that we need to look at kind of a more broad view on what kind of, specifically if we're talking about compilers and systems, what problems are we trying to solve, and how do we combine the program that we're trying to optimize with the programming model, the compiler, and the hardware. So maybe just one of the new domains that people are looking into is machine learning, and just writing simple C loops for representing matrix multiplication may not be the right solution, because we need to come up with new architectures, new accelerators, and then new programming models on top of it, and then compilers fit somewhere in the middle. And then on top of it, we need to come up with efficient applications. So if we're only looking at traditional C code, I think that compilers, there's still room for improvement in LVM and other compilers, but I think that when you look at a broader picture, then there's a lot of work to be done.
Yeah, that's actually a beautiful way to put it. So it's not only the compiler problem, right? It's just and what you're saying is that performance is not only the compiler's problem, right? So we should consider the whole system, right?
Yes.
Including hardware and everything. Yeah, that's a good point. Yeah, but any chance you think that we'll see some more sophisticated transformations in LLVM, like for example so right now compiler doesn't do any sophisticated things, like for example structure of arrays to array of structures and other data transformations. So any chance that we'll have some new interesting and sophisticated transformations in LLVM?
Maybe somebody could implement very localized transformations, but the problem is that the semantics of the programming languages don't allow this easily. When you look at the C programming language, there's clear semantics, and C or C++, and a lot of the basic operations are optimization barriers. Like you simply don't know what happens if you pass. You have to assume the worst. If you pass a pointer to some unknown function, when you look at the Unix environment, you can overload certain functions. So it's really a programming language problem that you're not allowed to do these things. If you were to design, so other programming models and programming languages would allow you to do these transformations. I worked on a little bit on this space in the context of machine learning, and it's exciting. You can do a lot when you have better representation, but I don't think that this is a kind of classic compiler problem. I think that Chris Latner calls it heroic optimizations, where we have to work really hard on analyzing this very specific case, and you can change in some cases the, let's say, memory layout, but then if you make a mistake, you get great performance cliffs. So I'm not optimistic.
Okay, cool. Yeah, that's great. GCC is still a very popular compiler, right? So it's still a default on many platforms.
Yes.
And this is actually what many people will naturally use, right? So do you think GCC compiler still has its own place, in the future?
Yes, GCC is a very good compiler. Many good people worked on GCC for many years, and it's very good both in terms of performance, language conformance. They recently had a major jump in warnings and usability. GCC is a very good compiler, and it's also good that there's competition in the compiler space. It's good that there's competition between GCC and LVM, and I have, even though I never contributed to GCC, I have a lot of respect for the people who worked on it and built it.
Right, that's good. Okay, so what do you think are the opportunities in the compiler space? So you obviously so you said that it's not only a compiler's job, right? So what are the opportunities for improving performance in the compiler space? Yeah.
Okay, so I mean, specifically, if you're talking about C compiler, you know, LVM GC or something that's related to compiling C, C++ code. So I don't know. There are a lot of people working in the space, a lot of smart people. They have good ideas. I can quote a lot of different ideas, a lot of good ideas. So one idea that's going around is the idea of having a high-level intermediate representation for C, C++. This is specific to the design of Clang, where at the moment there is no high-level intermediate representation. Both Swift and Rust have their high-level representation, Mir and Sil, and it allows the compiler to perform language-specific high-level optimizations that you can't do at the LVM level, because LVM it has very low-level representation, and by the time you lower your code to LVM, you lose a lot of semantics. So one of the ideas that's floating around in the industry is to implement this high-level intermediate representation. I believe that it will give good performance gains. I think that we may be able to hack it by adding attributes over the standard library and just defer inlining. But overall, I think it's a very good idea. And there are other very excellent ideas out there. The work that some people are doing with, let's say, super optimizers. There's work that's unrelated to performance on correctness. Let's see, what other ideas are there? I don't know. There are a lot of good ideas.
Yeah. So
yes.
do you think we will have
the interaction? Another idea: interaction between the compiler and libraries. I heard people talk about it in different circles, but basically, let's say you can make better use, or having profile-guided optimization can help you optimize underlying implementations of things like memcopy, malloc, things like that. Even maybe you can give hints to the operating system.
Right. Yeah, that's great. So, do you think that we'll see in the future, some compiler transformation, or maybe even the whole compiler steered by machine learning model?
Well, I'm sure. So people are actively working on it. So let's talk about what machine learning can and cannot do. So when it comes to actually doing the transformation, let's say assuming this decade's machine learning capabilities, I'm not expecting a machine learning neural network to generate assembly code. What the neural network can do is provide better cost models. So neural networks you may be able to feed a certain number of signals into a neural network, let's say, and then ask a question, should I inline this function? And then you feed in, let's say, the size of the function, the number of inputs, and a bunch of other signals. And then the neural network will be able to tell you whether you should inline it or not. Or another example, when you decide if you want to vectorize a certain function, a neural network may be able to more accurately predict the ideal vectorization factor, which means the width of the vector. Is it 8? Is it 4? And I've seen academic papers in this space, but I'm not expecting to be able to replace the entire compiler by one smart, big neural network that would emit assembly. That's not possible with today's technology.
Right. Yeah. So okay. So we'll get back to compilers probably many times during our conversation. But let's now talk about so how did you start working on systems and performance?
Okay. So a little bit about me. So my name is Nadav. I'm Israeli. I grew up in Israel. I have a wife and 3 daughters. We moved to Santa Clara about 10 years ago. My first job was in the Israeli army. Military service is mandatory in Israel. And I served there as a captain, as an officer for 6 years. And during my military service, I worked in the field of embedded computers, high performance computing. I wrote kernel drivers. I wrote Verilog for FPGAs. And then I worked in this space. I actually remember, so before I joined the army, I interviewed for a number of different military units. And the first, in my first interview, they asked me to optimize the pop count function. So they told me, hey, go ahead and implement code in C that counts the number of ones in an integer. And I remember that I wrote the code in C, and then they told me, now make it fast. And then I remember how I answered this question, and that was the beginning of my performance work, that interview question. Then over the years, I had to optimize, both in my military service and afterwards, I worked with systems that tend to be high performance. So if it's FPGAs or let's say a cluster of many computers that you need to distribute some workload efficiently. Overall, I had a lot of fun in the army. I met a lot of good people, very kind people who later opened very successful companies and contributed to the world in other ways too. And then throughout my career, I got to work with very smart people who taught me a lot of good things, a lot of cool tricks. So I worked in performance most of my career, and I love it. I enjoy it.
That's a great story. Yeah. So yeah. So you are the original author of the LLVM vectorizer, right? So tell us about the development of the vectorizer.
Okay, so I actually wrote 4 vectorizers over the years. The first one was the OpenCL vectorizer for Larrabee. We both worked at Intel, so I was working at Intel at the time, and Larrabee. So the name was Larrabee, and then when I worked on it, it was already Night Landing. It was the Intel GPU. So that was the first vectorizer, and then I worked on it when I joined Apple. I started working on it, and Schweig joined me, and other people joined me, and we started developing the vectorizer. There's actually a good chapter in your book about the vectorizer and how it works. I can go over it really quickly. The vectorizer has 3 parts. The first, you check the legality, under which conditions it's legal to vectorize a loop, and then afterwards you check profitability. And then after you do these things, you just go for it. And there's also an element of the cost model. You need to be able to ask the backend, what is the cost of a scalar add versus the cost of a vector add? And then you accumulate all of these things. So this was, so something else that's interesting is that I started by designing a very simple vectorizer. I had this philosophy that the vectorizer has to be simple. It has to work on relatively simple loops and simple cases. It shouldn't be doing heroic optimizations. Like if you're familiar with eigen or MKL, the goal is not to take, let's say, a matrix multiplication and have the vectorizer generate the most efficient code. This is the job for the library. So what I did is I started by looking at the GCC vectorizer, and they had a web page with all the examples that they support, and I went over these examples one by one. So a funny thing is that the GCC vectorizer was written by Dorit Nuzman at IBM in Haifa, and she was actually my neighbor in Israel, and I met her at the park, at the playground with the kids, and she's a wonderful person, and I followed her footsteps in terms of supporting the use cases in the vectorizer, and we added more use cases, such as predication and if conversion, unrolling. So this was the loop vectorizer, and afterwards I started and implemented the SLP vectorizer, which is different than the loop vectorizer. The SLP vectorizer basically tries to take scalars that float in space in the compute graph and then glue them together to create vectors. And the idea is that you look at you look for roots, such as, let's say, consecutive stores in memory or fin nodes that come after the other, and then you go up the tree and you try to construct a graph of vectors. And I still think, last time I looked at the code, I still think that there are a lot of opportunities for new places to start the search. I don't think that they added new routes or opportunities for searching the graph since I left, and this is something where there's still opportunity for performance. And then the last vectorizer is kind of a side project that I was doing. So I told you that I believe that the vectorizer has to be relatively simple. It shouldn't be doing things like SOA to AOS data layout transformations or tiling or all these things automatically. So in this research project, I implemented this domain-specific language where the semantics of the language allowed you to do all of these things, where you had clear semantics on where nothing could alias, and then the compiler had knowledge of the array structure, or the dimensions of the matrices, and then it was a pretty good compiler. It had a unique path manager that allowed you to backtrack and find the kind of the most optimal vectorization and memory layout. So it's a side project. So the name of this project was actually, Denis, you speak Russian. So the name of the project was Bystra. So what does it mean in Russian?
It's like a fast, right?
Yeah, so that exactly was the name of the project.
Nice.
So that was the fourth project.
It was cool. Was it based on LLVM?
Yes, of course. I mean, the vectorization was done at a higher level IR, but LVM was used for encoding and JITting and running everything.
Right. So what do you think about the other model? So so the vectorizer in LVM tries to discover vectorization opportunities, right? So what do you think about the other way? So like, for example, the ISPC model, where all the vectorization is explicit, right? So and everything is so every variable essentially is a vector by default, right? So this is how it works in ISPC. So do you think this model is superior than the auto-vectorization, than relying on auto-vectorization?
I mean, so first of all, I love it. It's a great model. The OpenSail has this model, also CUDA. It's this SPMD where you write the program, and the contract of that the language makes is that you should be able to always vectorize the program, the shaders, the kernel. GPU shaders use this model. It's a very powerful model. I love it. It fits certain domains. It's not going to give you, you're not going to be able to get more performance out of your, let's say, C++ compiler or spec benchmarks and all these things, but it fits certain domains very well. Graphics, machine learning, and the entire data pair model. So I love it.
Right. Yeah. Right. Okay. So let's talk about the performance work that you do at Facebook. So what is the importance of performance at Facebook? Why performance is so important for Facebook?
Okay. So Facebook has billions of users that use a bunch of different services, like the Facebook website, and then there's Instagram and WhatsApp. And it takes many computers to serve billions of users, right? And computers are expensive and they use a lot of power. So I work with a group of very talented people, smart people, on improving the performance of the server workloads. We have other teams working on client, on mobile devices. We focus on the performance of the servers. And I see that Amir joined the chat. He's one of the people I'm working with. So the idea is this. If you if you work on the compiler and you generate code that's 1% faster, then you can effectively reduce the size of your data center by 1%. And if you do it year over year for a long time, these numbers add up. And data centers are very expensive. In addition to reducing the size of data centers, you're also reducing the amount of electricity that you're using and your ecological footprint. So you make the world greener by running code that's more optimized. So in my personal life, I try to recycle, reuse, reduce my ecological footprint, but the kind of impact that we have at work is far greater because we optimize, a huge fleet of computers. And by the way, we upstream these changes to the open source. We work well with the open source community, and we give these changes to our partners and competitors. And I enjoy the fact that everybody become more efficient and waste less, resources and electricity. So
Right.
and
So would mm-hmm.
Oh, so one
Go
other
ahead,
thing.
please.
So there's a very good paper that describes the workload breakdown in Google data centers. I forgot the name of the paper. Kim Hazelwood is one of the authors of this paper, and it tells you about the workload breakdown at Google and how much time they're spending in protobuf, compression, malloc, memcopy, memset, all these things, and then the rest of the things is pretty much a flat profile. But it's a very good paper. If you want to know more about how time and resources are spent in data centers, I recommend looking up this paper.
Yeah. So this actually a great paper. Yeah, I agree. So do you work on the same flat profiles?
Do we work on flat profiles? Yes.
Yeah, so Google is, oh, I'm sorry. So the Facebook is a large distributed set of cloud applications, right? And I assume it also has the flat profile. So what are the challenges in such setup? And so because I assume that suddenly compiler doesn't play that that much that important role, right? Because simply have a flat profile.
Okay,
so what are the challenges, and what are the challenges and specifics, let's say, that you are facing?
Okay, so this is a hard problem, and luckily I get to work with very smart people who attack the problem from many directions, and I can give you a few examples. So we have folks working on Z standard. That's Jan Colette and other people working on Z standard, which is a decompression algorithm that's developed within Facebook. We make sure that we compress and both quickly and have good compression ratios. So that's one project. Another project is JE malloc. It's our own malloc implementation that was developed at Facebook, and it's pretty popular. It's used outside of the company by many open source projects. We're making sure that our memory allocations are efficient. We have great people working on the compiler, LVM, especially on things like working on profile guided optimizations and improving the scalability of link time optimizations, LTO. Pseudoprobes is one of the projects that they're working in, which is a better way, more precise way of doing profile guide optimizations. We have Bolt, which is a great optimizer. Maxim Pashenko and other people working on it. Amir, who's here, and which the LVM community recently accepted, and the team is working hard on upstreaming this binary optimizer to the open source. We have, and then we have a few other things that we're doing to improve the performance of the system. Like we're optimizing the C++ standard library and internal C++ libraries, and we're working on Rust. There's a few areas where we're investing. And it's not easy, but the people on the team are very smart and dedicated, and they're able to get more performance wins year after year after year. It's really impressive.
Yeah, that's actually great. So and then so thanks for you folks for open sourcing that. That's a really great set of tools. I've been personally using myself GE malloc and Bolt. So
Cool.
I also actually, so I remember once I tried to extract the code from HF sort. It was
Mm-hmm.
I remember it was integrated into HHVM, right?
HHVM, yes.
It was so tightly integrated in it. So I was having a hard time, extracting it and using it for my own purposes, because I didn't want to compile the whole HHVM, and frankly, I didn't know how to do that. So
yeah, yes, it uses Folly and the internal HHVM headers. Yes.
Yeah, so the tools are really great, and thanks for that. And yeah, and I'm looking forward to use Bolt as from the LLVM repository. That will be great. That's essentially a free speed up. I
can
don't
see
know,
that Dan. I see that Dan joined us. He's one of the people I mentioned that taught me cool things many years ago.
Yeah, great.
Welcome to the chat.
Yeah, welcome. Yeah, so again, guys, I encourage everyone to speak up. If you have something to say, then just request the mic. All right. So Nadav, tell me about what is your approach to performance tuning. So how do you start? How do you search for opportunities? Where do you start? What tools are you using?
Okay. All right, so we don't have a lot of time, so I can very quickly go over kind of few ideas and tricks that I use, and then some performance kind of guidelines. So kind of very, very quickly, I'll share with you my playbook. I'll go over this very, very quickly. So first of all, you need to come up with a kind of cost function. What do you care about? CPU time, latency, area on a chip, whatever it is, you need to figure out what you're trying to optimize. Now there are a few tricks that you can do to extract performance quickly. So first of all, you should do competitive analysis. If you're working on LLVM, compare yourself to GCC. See where you're better, where you're behind, and try to learn from the competition. This is always good. If you don't have a competition, compare yourself to the roofline, to the theoretical peak. What is your utilization? Are you at 50% utilization, 70% utilization? What would it take to get more? Now, I understand that this is very difficult because modern systems are very complex, but you can always do a kind of a rough estimate for the theoretical peak. The next thing is to visualize. You need to be able to create pretty graphs and spreadsheets on multiple workloads to see where you are. Look at the data, then look for the outliers. You can always learn from the outliers. And Excel or Google Spreadsheet, whatever it is, these are excellent tools. You should use them. Finding performance problems is similar to debugging. You need to slice on different dimensions. You can reduce the size of the program. You can bisect on revision number. If you're working on a compiler, you can disable certain passes, or you can actually disable the optimizer on certain functions. One of the tricks that I use is disable the optimizer on functions that start with the letter A, B, or C. Then this helped me to bisect certain things. Another trick that we have is you can always go one layer below. For example, let's say we're trying to optimize matrix multiplication that's implemented with 3 loops. Think about the layer below, which is a memory hierarchy. What are we doing to optimize for the memory hierarchy? And then other projects are doing similar things. Like let's say we mentioned Bolt. Redux is another example. You always try to optimize for one level below. In the case of Redux, which is a Java bytecode optimizer, the team is making sure that when you load the application, you read sequentially from the NAND, from the disk below. So there are things that you can do at your level, which are unintuitive, that make the level below more efficient. So these are kind of a few tricks, tips and tricks that I used over the years. If you want, I can talk about a few kind of engineering concepts or guidelines for performance. Would that be interesting to you, or?
Sure. Yeah. Please go ahead. I think we have time.
Okay. So this is going to be kind of very meta, but very high level. But I think that there are only a small number of things that you can do to get more performance. So the first one is to remove redundant work. So don't do the same computation twice. Don't, let's say, write logs that you're never going to read. Just remove redundant work. The second thing is that you need to batch things together. Do multiple things at once. If you're sending a packet over the network, create bigger packets instead of sending multiple packets. If you're performing computation, perform SIMD, vector arithmetic instead of one. So this is batching. The third concept is super powerful. This is look for sharp histograms. I think that sharp histograms it's at the base of so many different optimizations, like caches. Caches rely on the fact that you're accessing certain memory areas more frequently than others, or the fact that your encoding is not symmetrical, and some instructions are encoded with longer sequences and some are shorter sequences. Or if you were talking about JIT compilers, there's inline caches. So all of these things rely on sharp histograms. Not all the computations are distributed evenly. And then the next thing is that you can do to enable sharp histograms is disaggregation. So in the context of server, work on server, imagine if you were to run your web server and your database server on the same machine, that would not be great for your iCache, right? Because you'll create a flatter profile. But if you disaggregate, if you sort workloads according to some criteria, then you're creating for yourself very sharp histograms, and then you expose more opportunities. So that was number 4. Number 5, the last one, is that the key to performance is always parallelism. With the end of Dinard scaling 10 years ago, we're not seeing faster computers with higher frequency. So the only trick in the book is parallelism, really. The only thing that's left for us. So processors work really hard to extract parallelism with the out-of-order mechanism. But the accelerators, what they do is they basically they synthesize more multipliers and to enable parallelism, and you so just parallelize thing and allow more computation at the same time would give you performance. So these are kind of the high-level principles for approaching performance.
Cool.
Does that make sense?
Yeah,
I know it's kind of dense. It's
yeah, it's no. I think you essentially listed let's say the most frequent performance traps that people sometimes fall into, right? So like like don't do unnecessary work, like batch, let's say, for example, system calls, right? Like do more work in one unit, let's say, of like try to do more work in one let's say system call and stuff like that. So yeah, so any performance debugging stories you can tell?
Yes, I can tell one fun story. So I worked on this embedded system. It was a PowerPC chip that was embedded in an FPGA. It was Xilinx FPGA. And I wrote this really good kernel driver for a DMA piece of hardware that managed a bunch of buffers. And I was so proud of myself, and it worked really well, except that after a few minutes or maybe a few seconds, sometimes the system would slow down and the internal buffers on the FPGA would fill up, and we would spill information, and that was not good. And I worked on debugging the performance of this system for a while, and I was really frustrated. And what ended up is that we realized that when the system was writing logs, it was sending the logs through RS-232, through console. And for some reason, it locked the system. So when we were writing logs, and especially long messages, it kind of locked the processor, and then data came in, and it kind of blew up the internal queues. So the solution was to just not compile that driver into the system, and that solved the problem. So that's one fun story. Another fun story was, so this is going to be familiar for people who work with compilers. So I was working as a compiler engineer at Apple, and I had the task of looking at the Lua interpreter. Lua is a scripting language, and GCC was faster than LVM. And I tried to figure out how to make it faster. And like, how do you start? Like, the LVM compiler is 1 million lines of code. GCC is another 1 million lines of code. The Lua interpreter is also huge. And then there was also the input program, and everything is huge. How do you start? Well, I started by bisecting things. So first of all, or I'm sorry, not by bisecting, by deleting code. So I took the input script to the Lua program and I deleted most of it. So the benchmark was not correct anymore, but I was still able to reproduce the performance delta between GCC and LVM. All right, so I reduced size of the Lua script to something tiny, and then the same to the Lua interpreter. I took the C program, the Lua C program, and I started deleting code from the main interpreter. So the interpreter is a huge switch statement with that handles a bunch of opcodes. I started deleting cases that were not used until I got into kind of one opcode, one or two opcodes. But then I continued to delete code, and then I finally had a small enough program that I could that I could eyeball. So it was not the original program, but it was a program that exposed the difference between the code that GCC and LVM generated. It ended up being something like a partial register update problem where, again, modern CPUs, super complicated. The out of order mechanism tries to run ahead and compute, rename registers, compute things ahead of time. But if you're only updating half of a register, then the processor has to wait for the other half to complete before it can produce a result. So it was one of these things that small cogen could help the problem, but I enjoyed working on it. It was a lot of work, but it was fun. I learned from it.
Yeah, that's interesting. So this approach actually might not work on a big, spec 2017 or spec 2006 benchmark.
Yes, yes.
But it's funny. Yeah. So would the other approach, like when you would the more standard, let's say, approach of collecting the performance profile of a program, would this approach work for you, or?
What approach do you mean? Do you mean like using performance counters and?
No, I mean just collecting the hotspots information, then try to see the assembly difference, and then see what instructions are hot, and try to try to understand the difference in the code gen in the hot places.
Yes, sometimes it works. Sometimes it doesn't.
Yeah, sometimes it doesn't when you have too much of a difference, and it's probably usually the case where because the code generation might differs between two blocks. So.
And sometimes things are so fragile. Small changes in the code can change so many things. Like the branch predictor depends on the instruction pointer, and it uses it as a hash, and then you can't really predict the performance or how your prefetcher would behave. And there's a lot of noise in these systems, and not to mention turbo and address space randomization. And
yeah, that's true. So actually, one funny example I have is that well, I have let's call it pleasure of debugging a performance problem where the only difference was in the encoding of the instruction. So one instruction was using like something like XMM and XMM7 or something like, and the other instruction was using like XMM0, and that was the only difference in the code generation, and suddenly it caused the difference in the encoding of this instruction, and and then all these strange sort of things happen, and then suddenly it gives around 2 or 3% performance difference. So that this like one byte of encoding can cause so much of a performance difference. So this was it was a nightmare. Yeah.
Cool.
Yeah, but it's funny.
Oh, man.
All right. Let's see. So
I love it. So do you also do you enjoy doing these debugging, like performance debugging, or do you do like other aspects of performance engineering?
Yeah, sure, absolutely. Yeah, so I remember actually. So like I had so at some point I spent a lot of time really trying to figure out how we can better solve the code alignment issues. I spent maybe like 3 or 4 months, trying to tackle this problem, because I was trying to to figure out if there is any methodology that I can use to quickly identify if this is a problem with code alignment or not. So actually, let me start from the scratch probably. So for those who don't know what's the code alignment, is essentially when you lay out the program in memory, right? So certain functions have certain offsets in memory, right? And these and this offset essentially can specifically the offset of the hot loops can cause significant performance differences. In my let's say experience, I saw the situations where only when you let's say shift your loop by let's say 16 bytes in the memory layout, it can cause up to like 50% or 70% performance improvements. That's huge, like that, right? So that's a huge difference. So yeah, so I was I was trying to figure out what performance counters I can look at, and try to apply different layouts for different benchmarks, and based on my experience, I can tell that it's a really hard problem. And whenever, for example, I try to apply some alignment to all of the benchmarks, for example, in Spec 2017 or Spec 2006 suite, some benchmarks go up, some go down. So there's really no silver bullet. It's like as for me. So, but the good point here is that the CPU architects work very hard, to try to tackle this problem from their perspective, and they try to reduce the impact of this code alignment, because from compiler developer perspective, this is a really annoying problem.
It's I love these things. I have a big smile on my face right now. It's
yeah.
it reminds me, by the way. So Amir is here with us on the chat room. He told me a few weeks ago about something that he was optimizing, which is that macro fusion doesn't work across cache line boundary, and
right.
So he was telling me about this in his work. So it's cool. Amir, if you want to tell us, that'll be interesting.
Sure. Yeah. Okay. Amir is requesting. Let me approve. Okay, Amir, you can speak now. Hello, Amir. You want to tell something about microfusion?
Yes. Can you hear me now?
Yeah, we can
okay,
hear
great.
you.
I can chime in on performance effects of alignment. The most significant are, of course, when your working set fits into the cache or not. This is pretty obvious. But when dealing with the program, whether it fits into iCache or not, it depends on so many things. And specifically, Bolt tries to optimize the placement of the program so that the working set is arranged in memory so that the jumps are constrained to try to fit into the cache. Besides the hot-cold splitting of the program. So that's the major, perhaps the most major performance effect of the alignment and placement. There are many smaller effects such as, for instance, macro fusion, that it cannot happen across iCache cache lines. that is 64 bytes. So this CPU internal optimization will not kick in like 1 out of 64 cases statistically, but it also has an impact of a percentage of IPC, so that for a hot enough loop, it would be significant. So these are the examples that we're trying to optimize automatically with Bolt, but I'm sure there are other cases that cannot be dealt with automatically.
Cool. Yeah. Yeah, that's a really interesting, let's say area of compiler development. So that's and sometimes annoying when you try to to make some transformation, and this information is supposed to be doing good things only, and suddenly you see performance regressions in other places, and you're like, oh, like why? Like I like for example, right? So my optimization is not supposed to harm any other places, but unfortunately it doesn't, and many times it's the underlying reason for that is that there is a code alignment issue somewhere, or some other strange hardware effect in place.
I love it how every time one engineer talks about the war stories that they had in working on performance, the whole thing turns into a support group where people say, yes, I also had a case like that where I was trying to work on this workload and I had regressions elsewhere. And I love these discussions. It's really cool.
Yeah. So actually, by the way, so if anyone wants to share his or her story, then please speak up. We would love to hear your story.
May I ask a question before the war stories continue?
Sure.
It's just about LLVM. I was wondering, what would you say were the major issues that the efficiency sanitizer project ran into, and do you think it'll ever be resurrected?
Oh, well, efficiency sanitizer. I'm not aware about that.
ESAN for LLVM.
Oh, okay. So Nadav, you wanna go ahead? I actually haven't experienced myself working with it.
I remember reading about the ESAN a couple of years ago. I know that there was also work that was done on GCC, and there was also work that we did within Facebook. I can briefly talk about the motivation. It's and I can look up the name. There was an academic publication by some folks from Google. I think it was almost 10 years ago. But I can briefly go over the motivation. So imagine a simple loop. Let's say you're pushing something into a vector, STD vector, and you push and you push and you push, and the vector continues to grow and grow and grow. Now, the vector would continue to double its size, but before you get to a size, let's say 32, you would be doing 5 allocations and deallocations. So 5 calls to malloc and free, which are very expensive, or relative to the cost of just increasing the size of moving a few pointers. So this is one example where C++ code is inefficient because the user forgot to reserve the size of the vector to prevent these mallocs. Another example is when people pass things by value instead of by reference. So we worked on a project. So David Goldblatt, Lee House, and me worked on a project where we tried to instrument the C++ standard library and detect cases where there are inefficient uses of the C++ programming language, and we found that basically all of the top open source projects have inefficiencies. So for example, Bitcoin is really hot nowadays. They pass shared pointers by value all over the place. So you have the extra copies and atomic operations. And then we found stuff in in CMake, and we found stuff in Foley. We found stuff inside the C++ standard library itself. We fixed a few things in LVM, and so people make mistakes, and there is room for efficiency sanitizer. I think that one of the challenges is that for the really hot loops, people are using profilers and they're finding these cases and they're easily fixing them. But the tail of issues is very long. But I'm not sure what is if it has a good return on investment in terms of going and fixing all these cases. Because if you have a case where you're growing the vector too much, just when the application is launching, maybe it's not important to get rid of these five calls to malloc. I don't know, but in any case, it's an interesting case. It's an interesting problem.
Yeah. Okay. So since you talk about malloc and other stuff, so we talk a lot. We talked a lot about compilers today, right? But if we consider the whole stack, where do you see the biggest opportunities for performance improvements? Like hardware, operating systems, libraries, maybe application level itself.
I don't know, really. I mean, there are smart people working on all levels of the stack, and there are a lot of very good ideas that people have, and I don't know. I don't think that I have an answer here.
Okay, but if you were to predict, then
okay.
then where would you say will have the biggest performance gains coming from it? Or maybe you would say that it's not even the software, or maybe you would say there is a lot of opportunities in discovering new algorithms. Let's say like you said, for example, for machine learning, right? Machine learning is a very active area of research. Where the new algorithms are being invented, like probably every month or so. I don't know. So.
Okay, so let's see.
So what would be your prediction?
Well, it's hard to predict, but I would say so. Dinard scaling ended, so we're not seeing additional performance coming from the increase in frequency. Moore's law is slowing down. It's not that we are making progress, but each generation is becoming more expensive. So, and this makes the generations of hardware architectures or specific process technology, they make the generation longer. But we're still seeing progress there. It seems like the way to get more performance nowadays is with more cores, and I mean more parallelism, which is more cores and accelerators. So I mean, just like other people, I would expect to see more CPUs with more cores and see more parallelism. I guess that Rust is interesting because it gives you safety and parallelism at the same time. Machine learning is also interesting right now. The parallel architectures, accelerators and GPUs are the most efficient architectures for executing machine learning. Yes, I mean, you would see, so you're seeing bigger and bigger neural networks. GPT-3 is huge in terms of the number of parameters, but I don't think that we have new operators, new basic kind of linear algebra blocks. I don't think I've seen anything new since 2017 or something. We're still talking about convolutions and element-wise operations, or a combination of element-wise operations. So it's definitely an interesting space.
Can I ask a question? Actually, to both of you, Denise and Nadav, since you, Denise, work at Intel, maybe you know, the work that architects are doing, and Nadav, since you had an experience with FPGA and embedded programming, the question is, do you think the major performance breakthroughs may come from hardware-software co-design. I'm trying to hint to point to the progress that Apple is doing, since they control both the software and hardware. So what do you think, Denise and Nadav?
Go ahead,
Nadav, you want to go? Oh, okay, me. Okay.
Yes.
So the yeah, I mean, the hard question, right? And so the hardware software co-design is definitely great. Yeah. So the Apple is able to optimize the entire stack. So that's obviously great for them. Yeah. So Intel, for example, is also collaborating a lot on the Linux kernel, and then we have a bunch of developers contributing to the kernel. So that's definitely an important let's say cooperation. I would say like that. So the definitely answer is yes. That's important part, and also I think that's not only let's say the part of the solution. Another part of the solution is is coming up with the great programming model, and especially with emerging with new hardware accelerators emerged every day. We have a whole bunch of accelerators already, and it's the programming model for one accelerator might not necessarily fit the other accelerators, right? So that's, for example, why Intel started the One API project. Is just the idea is that there is no nowadays there is no one good programming model to program every device on the planet, right? The CUDA is a great approach, but this is only a proprietary solution, right? So where One API is completely open sourced, and then the idea is that we will hopefully be able to program every hardware, no matter if it's a FPGA or GPU or neural network processing unit or visual processing unit, whatever. We'll be able to program it using the one single programming model. So that's the promise. Yeah, so I'm not sure if that answers your question, Amir. So Nadav, if you want to add to that.
Yeah, so I was going to say that vertical integration and hardware-software co-design is really important, but then there's also the force in the other direction, which is the economy of scale. So when you have many customers, you can invest more money, you can hire more engineers who would file every single register in your processor to make sure that you can perform arithmetic floating point multiplication in 3 cycles instead of 4 cycles, and things could be more optimized because you have more money. And it's funny to me that the industry goes back and forth between vertically integrated companies and then companies that serve as a foundation for many other companies. And experts always say, well, of course, Apple's doing well because they're vertically integrated. They can get amazing performance wins. And then when the pendulum swings in the other direction, they say, well, of course, you have the economy of scale. You can spend more money on the process technology. So I think both are valid answers here. And both are very strong forces.
Right. Okay. So let's now talk about different programming languages. So Nadav, you worked on different languages, including C++, Rust, and Swift. So do you think it's reasonable to compare their performance?
Okay, so I worked with Rust as a user. I never hacked on the compiler, but I did work on JavaScript. So, I mean, they have some similarities, some differences. Swift and Rust are relatively similar, and they're somewhat close to C++. JavaScript is very different, and they have different solutions. I mean, to accelerate JavaScript, people came up with very sophisticated JIT compilers. To accelerate or to make C++ fast, people came up with good static compilers. And then for Swift and Rust, you have the high-level optimizer on top of LLVM. And all of these things are very interesting.
Okay, so some of the things you can talk about that one language has done right, while there is the opportunity to do the same in another language.
Okay, so it's very interesting, but the thing is, different languages have different constraints. So C++ became popular because it was an extension to C, and they had to inherit all the baggage that C had and the unsafety and all these things. By the way, Swift also had to be compatible with Objective-C, and that influenced the design, but it was played out in a very good, in a good way that they basically morphed Objective-C before they created Swift. And then JavaScript, they have their own constraints because it's a language that runs in a browser, and they also have their legacy. I really like Rust. It has great syntax, great tools. The IDE works well. Cargo and Clippy are amazing. It's sometimes non-intuitive. When I was first starting to program in Rust, I would get these errors where the borrow checker, the compiler would tell me, well, you can't mutate this vector while holding a reference to an element. I was like, wow, what do you mean? And I would get enraged, but then I would realize, yeah, of course, yes, the compiler is right. It's not safe because the underlying memory could reallocate. So it's a good programming language. I like Rust. JavaScript is becoming a better programming language, but so here's a thought that I have. I feel like many of these languages came up with new and unique features. Some of the features would live on, and other features would die. For example, in Python, you have the indentation syntax that I don't think any other programming language since had adopted this because it's probably not a good idea. JavaScript has the prototype chain, which is their way of implementing of their way of doing inheritance, which is crazy and creates a lot of complication in JIT compilers. I don't think anybody else implemented it since. C++ has multiple inheritance, which well, C++ has a bunch of features. Swift is also a big programming language, but the designers overall have good taste, and we're able to kind of make sure that the experience is consistent. Yes.
Yeah, that's great. So if we go back to the example that you showed previously, where you push back into a vector in the loop, right? And then so obviously the missing part here is that the programmer should reserve the memory in advance, right? So in order to eliminate the need to call malloc multiple times. And I assume this is a problem where the C++ language can or maybe and let's say a language and the compiler can where the compiler can help and maybe there could be also some support from the language. So do you think that this problem can be or maybe it there is already a good solution in another language, for example, I don't know, to help a programmer to prevent such kind of performance traps?
Yes. So this reminds me of another problem. So let's take a step back and say it's hard to fit it. So to add the reserve keyword automatically, you need to rely on some profile guided optimization, and it's really hard to do, especially if you're developing a library that's used in multiple different contexts with multiple callers. And so how do you do that? Like, how do you figure out this parameter? Do you reserve vector size of 10 or 32 or whatever it is? And this reminds me of another problem. You mentioned that we would like to have machine learning as part of a compiler. And machine learning neural networks have weights or parameters associated. So also, how do you train and keep these weights up to date? So this is similar to the problem of deciding on the parameters that would that control the size of the vector that you would like to allocate. And I don't have a good answer. I mean, right now it's I mean, I don't know. I don't even have a direction of how to think about it. Do you have an idea of how to solve it?
No. So maybe like one of the solution would be as you said previously, right? So come up with some high level IR that will capture the semantics and then we can go from there because.
But at some point you need to come up with a parameter. Are you reserving a vector size 5 or 32? And then what do? Do you check it into the code, or do you put it as a configuration file on the side? And how do you update it when the profile changes? I mean, if you change another side of the program and then you call this function with smaller inputs or bigger inputs, how do you retune it?
I see.
I can chime in. Can I bring up something?
Sure.
So, you know, this topic of reoptimizing the code, actually both profiling and reoptimizing, the first thing that comes to my mind is dynamic binary translation systems that were developed in many places. The most famous is Transmeta, and well, you know that the idea is the processor can profile whatever is running and translate it and optimize it on the fly. But it doesn't help with, as you mentioned, higher level constructs such as pre-allocating a buffer, right? One possible solution, actually, I've seen papers on that topic, is the tighter integration between underlying binary translation system with higher level IR. For instance, for Java with the binary translator. So the CPU can expose a device that would be used for higher level IR, which can be then mutated and optimized. So I think it's a promising way to re-optimize code, but I don't think it's an economical way, because none of the dynamic binary translators that were deployed in hardware live on right now. For some reason, they are not. The industry did not catch up with this idea. Maybe it would be abandoned. Maybe it would be resurrected at some later point if performance outweighs the costs of carrying a DBT system on a CPU.
That's interesting. So I actually heard about Transmeta, and I heard about the whole idea of the hardware recompiles and reoptimizes the binary on the fly, but can you please tell me more about it, because that sounds really interesting. So like, do you end up integrating the the whole compiler into the CPU, or let's say the whole optimizer into the CPU, or how it works?
How dynamic binary translation systems work is that the CPU is equipped with profiling mechanisms that help it identify hotspots. And from there, the CPU can create an internal representation of the code, like copy the code from memory into some reserved memory that no one can access besides the CPU itself. And equipped with the profile information, it can perform various optimizations that compilers can do, such as constant propagation. If the CPU knows that this load from memory, like let's say it returns the same value all the time, it can easily do value prediction, let's say, and just replace the load with a constant and propagate the constant throughout the region. So that's one example that I'm making up because I don't know if I can go over any specific systems. So
Okay, so this, so
yeah.
okay. Sorry. So it sounds a lot like a Java hotspot compiler, where they essentially doing all those sort of things, right?
Yeah.
So okay, and then so probably the JIT compiler can do it more easily, right? I suppose there is some specific use case that I don't know yet, where this binary translation really shines.
Okay, where it really shines is exactly in the domain of hardware-software co-design, because there are many limitations with existing instruction sets. Well, the most obvious case is x86, where it carries a lot of legacy that people don't like. As Nadav mentioned, there was partial register rewrite that is causing microarchitectural stalls. So if you're designing a better ISA, you can work around those issues. And that's where dynamic binary translator can seamlessly translate from existing or legacy ISA to a new and better ISA, which maybe it can have more registers, maybe it can expose microfusion that would be done implicitly. It can expose it for the compiler. So it can perhaps add the features like transactional execution that Intel is adding, like use it automatically to gain some extra performance. So that's the premise, that it can maintain compatibility while leveraging better ISA to gain more performance.
Cool. Yeah, thanks. So, by the way, guys, do you think there is any chance that we can have a JIT compilation in C++? Like, and the profiler integrated in the compiler, like for example, so to mimic the Java hotspot compiler. Or it's
there is a project like that.
Idea.
It's the Cling project. It's basically an interpreter for C++.
Right, but there is no integrated profiler and the reoptimizer in the runtime, right?
Yes. Could be interesting.
I can imagine Bolt to be added, but enhanced to cover that use case, maybe in the future, once it's in LVM and people find this idea interesting. It would be possible to come up with a runtime for C++ that for C++ programs that would profile the program and optimize it on the fly. I think it's doable because DBT systems for assembly exist, and there's nothing preventing this idea being applied on C++, I think.
Yeah, it may be harder than actually. So the problem may sound So the problem probably is is harder than we think, because you also need to preserve all the language semantics, and while you're running and have only the binary code, it's not easy to capture really the high level semantics of the program. Okay. All right. Okay. So unless anyone has any other comments, we'll probably wrap up. I have a few more questions to Nadav, but if someone wants to stay in this topic and have, okay, we have additional comments. Let's see. Okay, Damage Boy, I'm improving. Oh, hello. Hi, Damage Boy, you can speak now.
Okay, then I guess you can hear me now.
Yes.
Yeah.
So I just wanted to mention about this so-called wishful thinking about C++ and JIT. So there was, I'm pretty sure it's stuck somewhere in nowhere land right now. But Hal Finkel, who used to work in Argonne National Laboratories, has a LLVM fork with some experimental work around this, where you could actually do JIT with LLVM on the fly. You can find it on his GitHub page, and he had a talk in the LLVM dev meeting a couple of years ago.
Oh, yes. Yeah, and he was talking about JITting templates in C++. That's right.
Exactly. Yeah, which is kind of like a dream for me at some point.
Yeah, it is actually a dream for me as well. So do you know if this idea took off and
So I actually did it a lot myself in C#, which was a lot of fun to be able to specialize to that level. So the concept is something that I'm very familiar with, and I like it, but I never did it. I never did it in C++ at all.
Okay, cool. Yeah, this would be nice to have. Okay, so Nadav, do you have any teasers on, or something that Facebook or you are particularly are working on?
In what area?
In any area, maybe you are secretly working on some Bolt like tool or any other breakthrough project that you can share or tease now.
So people at Facebook are working on a number of very interesting projects. I mean, a lot of cool projects, and we usually open source these projects when they mature. I have a few side projects at home, but nothing that's that's ready to be open source in the context of performance.
Okay.
Amir, you oh, sorry.
Yeah, please go ahead.
Oh, I was just going to say that Amir made a hint at something that seems a bit more significant than he may have emphasized, which is the importance of managing the difference between the chips that are actually being manufactured and the ones that are required to solve the performance problems that are presented either by the languages that are already part of the legacy or the languages that are just now appearing. And what I was wondering, given the advanced perspective that you have, is whether or not there really is a effective trade-off between that hardware liability and these software level performance analyses. In other words, is it what's it going to take to change the chip makers so that they stop introducing unnecessary burdens on further development? Like, is every company that has to do a computation going to have to make their own chips internally in order to start dealing with the bottleneck at the appropriate scale?
Is this question addressed to me or the host or Nadav?
I just I guess anyone with a relevant perspective. I'm
Okay.
just trying to, because one of the things that I'm noticing in this conversation is that there's cultural baggage that if you could somehow flip a switch and change cultural practices, you would do that immediately, and it would be based around the practices people keep when it comes to constructing the hardware under the consideration of the software that it's going to run. And I'm just confused as to how does performance analysis at the software level matter when the legacy of the hardware is such a severe bottleneck?
I can say something on that topic. Actually, well, a disclaimer. I used to work at Intel on hardware software co-design projects that were R&D-like in nature. And specifically, we were looking at the performance of existing software on new CPUs, like on prototype architectures. And the premise, I think, that you have in the question is that existing hardware may not be really well suited for new software, or there might be bottlenecks in the legacy, in backwards compatibility. But I don't think it's true, because the CPUs nowadays are really, really huge. Like, there are billions of transistors in them, and the area impact of backwards compatibility for x86 is not large. It's pretty small. The main driver of performance is the number of transistors that is allocated to out-of-order mechanism, to ROB, reservation stations, number of physical registers, execution units, memory, bandwidth, and stuff like that. And modern chips from different vendors, they're pretty similar, and they achieve similar performance. So it's unlikely that by stripping the legacy, we might get better performance on the software. I think, yeah.
I think
I agree, by the way.
Yeah, so
I agree. I mean, the front end is less than 30% of power consumption. And
sorry, what was that?
yes, I agree with Amir.
What was that about the power consumption?
The front end, yeah, the front end of the processor takes less than 30% of power consumption, and this includes both fetching and decoding. And so even if you migrate from the x86 instruction sets to something else, you're not likely to get major performance wins, which goes along. So it agrees with what Amir said about the efficiency of the overall processor, which is not bottlenecked by the instruction set.
So then what is the reason that people are interested in field programmable gate arrays then?
Oh, FPGAs are a completely different thing. On an FPGA, you can synthesize your own circuit. You can synthesize, 100 multipliers if you want to. Maybe multipliers is not a good example, because you do have ASIC components on the FPGAs. But let's say that you can synthesize any number of memory banks which are equivalent to local registers, or you can create pipelined computation that operate at the same time. When you execute instructions on a processor, you execute, if you ignore the out-of-order mechanism, it's on the order of 1 or 2 or 3 instructions at once. But if you create pipelined circuit on an FPGA, the whole thing operates at the same time. So it's a completely different thing, FPGAs.
Well, I guess there's also another thing that I didn't make specific, which was the question of performance, as you brought up, measured in terms of, for example, like the picojoules per computation or per operation of the machine, and that being another possible constraint on the kinds of languages that end up getting selected. But I guess actually I'm a little confused as to whether or not. So why is it specifically that field programmable gate arrays shouldn't be compared to the performance of a CPU when we're talking about performance analysis for specific problems?
Well, let me chime in. So I think well, I mean, comparing performance between different hardwares, well, it's hard, right? And then so FPGA is essentially an end game when you have a known workload, right? When you have a fixed program, right, where the code is never changed, then you essentially you can put it in stone and and program it in FPGA or ASIC, and then and then you have and then you can have and then you can predict the latency of this program, like down to the exact number of cycles. So that's that's probably the most frequently use case for FPGAs, right?
Well, I mean, that's the use case up to this point with most of them. Yeah, so a lot of the conversation up to this point has been about the way that things have been in the past going forward, rather than imagining something that would be entirely different from the present situation and carrying whatever principles we have about performance analysis into some different situation. I guess I was trying to extend the conversation beyond just this is performance analysis as it is now into something that's not like today. And in that possible future I'm contemplating, there's a careful a synthesis between the general purpose CPU and the special purpose field programmable gate array. And in fact, this is not so much an imaginary future as it is an actual one. There's a very concrete example of a kind of midpoint between field programmable gate array and full-blown CPU. And it's a very unique chipset called the Green Array Gate 144. And it's created by, of all people, a strange man called Charles Moore, the inventor of Forth. And it's a little bit unique in that it's about 144 miniature chips on a single chip, and they have these kind of specialized jobs between them. And there's just been some surprisingly interesting things that you can do when you have things halfway between a CPU and halfway between a field programmable gate array. And I was hoping to hear something from either Amir or Nadav, or sorry, I don't know, I apologize for pronouncing, but something new and interesting closer along those lines, and then how performance analysis applies in those circumstances.
I don't know. I mean, there are many points on the spectrum between FPGAs and processors.
I haven't heard.
Modern FPGAs have ALU circuits that are and memory banks that are baked in.
Hello?
Hey,
Yes, go ahead,
Nadav,
please.
you are breaking up. Yeah, so. Mhm. Hello, Mark, please go ahead.
Oh, okay. I haven't heard of the project that the person who asked the original question. I haven't heard of that, and I would
Oh,
love to
sorry.
look.
That is John. My name's John. I apologize.
Okay, John. I haven't heard the project that you were just speaking about, John, but I agree with you on that whole midway thing as far as dealing with latency and power consumption with general purpose processors, because the majority of the latency and power issues comes from the fact that we have to bring data from memory to the CPU in order for the compute to happen.
Yes, exactly.
Right. So that's where a lot of the power and latency drain comes from in general processing, the von Neumann type of systems that we predominantly have today. So one project that I have been trying to follow is, I don't know if you've heard about this one, John, about from UpMem, where they have simple cores on the DIMMs themselves, so that you don't have to bring memory all the way back to the main CPU to do computation. You have some computation happening on the DIMMs themselves, so you can like offload a lot of the computation right to where the data actually is.
Yes.
Yeah.
So how do you spell that project?
UPMEM, UpMem.
Okay. Yeah. So, yeah, I'm trying to figure out a way of asking. So my problem is I don't have the same professional background as Amir and Nadav, and so we're having trouble crossing a language barrier. And I was trying to pose the problem by talking about something that they were a little bit more familiar with, but no, there are plenty of examples, and the reason I was bringing them up specifically is to help get a better definition of the principles of performance analysis that are independent of our current expectations for what's possible with the design of chips. So in the green gate arrays, these are composed of 144. They're called F18A chips, and each of them is a complete. It has RAM, ROM, and then it has a data stack. It has a return stack. It has an address register, and then it has 4 directional ports, 5 on some of the points, and they are in a 2-dimensional grid, and they are fully asynchronous. Also, there's a few different reasons why that's the case, but the way you compose things for it is you essentially draw up a floor plan that and you assign to a given region of the floor plan the function or the operation that you want it to compute. So there's beautiful 3-4 years ago, a beautiful thing that Charles Moore had constructed called Etherforth, and it was a complete development environment on the GA144 chip for programming Etherforth, and so each of the components for running the VGA output, for interpreting the USB keyboard, and all of this fit onto this floor plan and was factored into different sections. And the principles of performance analysis that are familiar for a world built in like a C or C++ situation just completely break down when you're trying to figure out what's going on. And it immediately appears that the only measure that matters is the picojoules per computation. When you're trying to figure out what is it that we're profiling ultimately, and is it practical to talk about it at that resolution? Sorry, I haven't asked a question there. I guess I've just kind of told a bit of a story.
So it's okay. It's okay.
Yeah, it's okay. So John, Mark, and others. So how about we have maybe a separate discussion to those questions that you have, John?
Yeah,
Does
sorry,
that
I apologize.
sounds
I
good?
apologize for
No,
hijacking.
that's fine.
Yeah.
No, that's completely fine. This we are here for exchanging ideas. So I really appreciate your speaking up and by the way, if you can then somehow DM me probably the links for the project that you were talking about, I would be really interested to taking a look into
Yeah,
that.
I could definitely do that, and I'll be sure to share with you, Mark, if you don't mind sharing me the same link. Yeah. Sorry, I just totally tried to hijack. I was hoping that we would hear something more about that. So the binary. You were talking about using machine learning in order to deal with compiling on different architectures for the same C++ program, and it's a much easier problem if you're just not using C++ or you're just not using the standard architectures. And the question I was trying to bring up when I said changing the culture is, what would it take in order to change the environment rather than changing the languages that we're using to solve the problems, to change the whole perspective from which the problems come. And this machine that I mentioned is just an example of the kind of things that you get when you just throw everything traditional out for a bit and start over and then try to solve the problem. But anyway, I'll be quiet now.
Okay. So I think it's probably the time to wrap up our conversation. Just let me ask you the final advice, Nadav. Let's start with you, Nadav. So tell us what you are using to educate yourself. So any books recommendations, podcasts that you are listening to, blogs that you are following, etc.
Oh. Yes, so I can give a few recommendations for. So there are good guides for modern architectures. It's a book that talks about Fortran compiling and loop optimizations. It's a very good book. There's the classic architecture quantitative approach. It tells you about the internals of modern processors and anything from the instruction set to the out of order machine. There's the excellent system performance book by Brent and Greg. The book that talks about dtrace, eBPF, and there are a few other good books. And then I also, I read online, and then I also work with very smart people, and I talk to very smart people, and I learn from them. So, yeah, there are many good resources out there. Good people, good books.
Yeah. So, any non-technical recommendations, outside, of compilers and performance? Any other resources you can recommend?
Are you asking about performance work or unrelated?
No, actually, not non-technical. Non-technical.
Oh, non-technical. I do a lot of other things. I'm a runner, so I run and I practice and I watch YouTube videos on how to improve. I'm learning Russian, so I'm reading short stories in Russian on my Kindle. I follow machine learning, so I'm reading papers from archive. Life is full of interesting things. So, yes.
Sure.
I definitely recommend continuing to learn. And
that's a great way to end the conversation. Yeah. Well, Nadav, it's been great talking to you today. I would love to see you joining us next time. To everyone else in the room, thanks for being with us, and see you in 2 weeks. And happy performance tuning.
Thank you, Denis. It was good to chat with you and everybody else today.
Sure. Yeah. It was a fun conversation. Thanks a lot. Bye.